All right, so lecture two. Today we're going to go over more terminologies and kind of vocabularies to differential equations, so that we get ourselves familiar with the terminologies, and therefore later on we'll be comfortable with kind of like the language we are using, the conversations we're going to have when we get to solving differential equations. All right, so what are the learning objectives? So hopefully at the end of today's lecture, of this particular lecture, I'm going to be able to verify whether a given function is a solution to a differential equation or the solutions to initial value problems. You could be able to distinguish between general and particular solutions. We're going to go over those definitions later. Identify explicit and implicit solution forms. This type of definition you may have seen before already. It's just that we didn't form what you saw this way. Right. And at the end, we're going to formulate an initial value problem or initial value problems. So lecture one, lecture two, and lecture three, there's a lot of terminologies, new things that you need to consume, but hopefully it's not too bad for you. All right. So terminologies, first of all, is the solutions to an ordinary differential equation. Again, ODE means ordinary differential equations. So a solutions to an ODE is the function that satisfies differential equations. So very similar to what you have seen when you took college algebra or pre-calculus. To verify a solution is a function, or a value is a solution to an equation. You just basically substitute that value that you have, or the function that you have, back into the equation, and hopefully you obtain a true statement at the end. So that's how you verify a solution. Right? Similar to that, in the case of ordinary differential equations, you have a function and you want to know if the function is the solution to a differential equation. Basically, just substitute that function into the ordinary differential equation. If you get a true statement, then you conclude that the solution or the function satisfies a differential equation. If you get a false statement, right, left-hand side does not equal to the right-hand side, then you conclude that the function is not a solution to the differential equations. It depends on the scenario that we're talking about. You may have a different type of solutions. But when you have a differential equation, you solve for the solution of differential equation. The first type of solutions you're going to get is called the general solutions. Okay. These are the solutions to the differential equation involving arbitrary constant c, right? You remember when you do antiderivative, the antiderivative give you a family of functions, right? So for example, if you have the integral of x dx, the answer to this is 1/2 x squared plus a constant c, right? So basically, this one is a family of function because capital C is an arbitrary constant. You don't know the exact value of C. Right? And this is called the general antiderivative, so that you learn in Calculus 1 and Calculus 2. There's another name for this in the context of differential equations. Right? Let's say you have the case of dy dx equal to, let's say, x. Something like that. And eventually you get y of x equal to capital F of x plus a constant c. Right? We will learn how to do this, but you integrate both sides of this equation, right? And you get the general solutions, or the general antiderivative. Again, the idea of general solution is that you have a plus c at the end. You don't know the exact value of the plus c, or the value of c. Therefore, this is called the general solutions or family of functions. Now, later on, again, we're going to look at different type of differential equations and initial value problem. If you know an initial conditions, right, or the initial value, then you can solve for the value of c explicitly. When you know the exact value of c, the general solutions plus the exact value of c, then you have something called particular solution. Okay. One of the example I usually bring up for this type of a solution is that you want to drop a ball. You drop the ball, you didn't give the initial velocity, or the initial velocity is equal to 0. But when you throw a ball, you kind of give a initial conditions or initial velocity. Right. So either case, you know the exact value, you would be able to find the exact value of c. Now, what is the initial condition? So initial condition is the conditions to the function at a designated time. Okay, So either you have at the beginning of an experiment, you drop the ball, right? So that's the initial condition. At the beginning of the experiment, you throw the ball, right? You give the initial velocity. That is the initial condition. Okay. So right here, I have a picture that illustrates that general solutions versus particular solutions. So all of this curve that you see here is a family of functions, okay, or the general solutions. Now, with a specific c, value of c, I'm going to arrive at particular solution. Okay. So I want to annotate this a little bit. That is what you see here. So the curve represents one parameter family of functions. Or in other words, this is the general solution. What does it mean for one parameter? Because there's only one thing that we need to care about that actually you don't know the exact value yet. That is the plus c, or the value of c. So that's why it's called the one parameter family of functions. And with this setup, it's called the general solutions. Now, when you know a specific value of c, you arrive at particular solutions. Okay, so hopefully you could be able to distinguish between general solutions and particular solutions. Okay, so in here, all of this curve combined together to represent a one parameter family of functions. Now, with a specific value of c, right, you have a pink curve, you have a blue curve, you have a yellow, green curve. Each of this is a particular solution. Okay. Now, graphically, that's how you be able to identify general solutions and particular solutions. And of course, later on, we're gonna solve solve for the general solution and particular solutions analytically using solution methods. Now, for example one, I want to verify certain thing, right? Verify that the indicated function is the solution to the given differential equations on the interval from -infinity to +infinity. So let me do problem A first. So what you do is very straightforward. You substitute what you have into the left-hand side of the differential equation and also the right-hand side of the differential equations. And hopefully you get the true statement out of this verification. All right. So the function is given in this case is y equal to 1 over 16 times x to the fourth. Right? The one with the y of 0 equal to 0, I'm going to do that later. But let's start with y equal to 1 over 16 times x to the fourth. So I'm going to start with the left-hand side and with the right-hand side, and hopefully you get the same answer. So for the left-hand side, you get dy dx. That means you're going to take the derivative on both sides of this function. And when you take derivative with respect to x on both sides of this function, you're going to have 1 over 16 times 4 times x to the third power. And simplify it, you get 1 over 4 times x cubed. So that's the left-hand side. Now for the right-hand side, you get x times y to the 1/2, with the square root of y. And y is equal to 1 over 16 times x to the fourth. So it's x times 1 over 16 times x to the fourth. Take the square root of that. And because the initial conditions here, so this is the initial conditions, is at x equal to 0. So therefore, we don't have to worry about a negative value out of the square root. Okay. So when you take a square root of 1 over 16 times x to the fourth, you get 1 over 4 times x squared. And then take x times x squared, you get x cubed. So 1/4 times x cubed. And this showed that this calculation shows that the left-hand side equal to the right-hand side, and therefore you conclude that the function, the given function, satisfies differential equations. So you conclude that since the left-hand side equal to the right-hand side, y equal to 1 over 16 times x to the fourth is a solution to the differential equations. Okay. In addition to that, you are given an initial condition, so you want to verify that the function also satisfies the initial condition as well. So it's very straightforward, right? So x is equal to 0, substitute x into the function, and hopefully you get y equal to 0, and that is very obvious that we do have that. So since x is equal to 0, y equal to 1 over 16 times 0 to the fourth equal to 0. So the function, the given function, also satisfied the initial conditions. So we conclude that the given function satisfies the initial condition. Now move on to problem B. You have a second order differential equations. Again, the second order because the highest derivative in the equation is 2. Right? We have a second derivative here. Therefore, second order differential equations. And the given function, y equal to x times e to the x. So to verify this function satisfies the given differential equation, you just basically substitute y prime and y double prime into the differential equation, and hopefully again you get the true statement. All right, so given y, you need to find y prime, you need to find y double prime. Because y is given as a product of two functions, x and e to the x, you need to apply a product rule for y prime. So y prime is equal to 1 times e to the x plus x times e to the x, which is e to the x plus x times e to the x. And from here, you take the second derivative to get the following. The derivative of e to the x is just e to the x. The derivative of a product here, again, you need to apply product rule. You have e to the x plus x times e to the x. And then simplify what you just obtained here to get the final answer. So e to the x, 2 times e to the x plus x times e to the x. Then you substitute y prime, and y double prime into the differential equations. We get that 2 times e to the x plus x times e to the x. So second derivative, substituting here. First derivative answer, substituting this. And then y is given. Minus 2 times y prime, which is e to the x plus x times e to the x. Plus y is equal to x times e to the x. Sorry. So this is just the left-hand side. Now you simplify the left-hand side. What do you get? So you have e to the x times e to the x, another x times e to the x. So you have 2 of those. Minus 2 times e to the x minus 2 times x times e to the x. And you see that 2 times e to the x cancel out with negative 2 e to the x. And 2x e to the x cancel out with negative 2 times x e to the x. And you get 0. And that is true, right? It's matched with the right-hand side, and therefore you say that the given function satisfies the differential equation. And or you can say that y equal to x times e to the x is the solutions to the differential equations. This implies that y equal to x times e to the x is a solution to the differential equation. Now, problem C, very similar procedure, but here we twist the problem a little bit. So this general solution to the second order differential equation is in the form of C1 times e to the rx plus C2. Can you find the value of r in this case, given the differential equation is 5 times y double prime equal to 2 times y prime? Again, very straightforward procedure. Given y, find y prime and find y double prime, substitute those into the differential equation and solve for r. So this is similar, very similar to one of the questions that we have on web work, right, on the online homework. Okay. And also, you're going to see this particular type of solutions later when we get to the second order differential equation, a very specific one here. So again, given y, you need to find y prime. So derivative of the first term. So in this case, C1 and C2 are constant, and R is also constant, and R is what we're looking for in this problem. So derivative of the first term will give me C1 times R times e to the Rx. Derivative of C2, since C2 by itself is constant, derivative of that is 0, so I'm not going to write it down. So if the first derivative gives you this value, C1 times R times e to the Rx. And what about the second derivative? Given the first derivative, the second derivative is C1 times R. Take derivative of e to the Rx, you have R times e to the Rx. Therefore, you got C1 times R squared times e to the Rx. So we're done with derivatives. Substitute this derivative into differential equations. So substitute y prime and y double prime into the differential equation. We get that the left-hand side is 5 times C1 times R squared times e to the Rx equal to 2 times y prime, so 2 times C1R e to the Rx. So C1 is constant and non-zero constant, so you cancel that out. E to the Rx cannot be equal to 0, so we're just going to cancel that one out as well. And you're left with just 5R squared equal to 2R. Okay. Now you're going to move everything to one side of the equation to solve for the value of R. So 5R squared minus 2R equal to 0. You factor out the R, and you're left with, so R times 5R minus 2 equal to 0. And from here, you either have R equal to 0 or 5R minus 2 equal to 0, or R is equal to 2/5. So there are two solutions to the value of R. One is 0, the other one is 2/5. Okay. So when you see something like this, you always have to move everything to one side of the equations, factor out the value of R, right? Because R in this case is the value that you're looking for. So in a way, it's a variable, so you cannot just cancel that out, right? Even though it's a constant at the end, but still a variable in the context of solving that equation. So you have to be careful with that. Now, next two terminologies relate to explicit solutions or implicit solutions. So explicit solutions are expressed explicitly in terms of the independent variable. The opposite of that is implicit solutions. So the solutions are not expressed explicitly in terms of independent variables. So I have a circle here. The circle can be broken down into two different pieces. The top one, top hemisphere, and the bottom one, bottom hemisphere, so semicircle. So the equation of circle, in this case, the circle center at the origin with radius 5. So the equation of circle given as x squared plus y squared equal to 25. So this solution or this equation is not expressed in terms of, or expressed explicitly in terms of independent variable. Okay, therefore, this type of solution or this type of equation is called implicit solutions. So this is implicit solution. In addition to that, you have, of course, explicit solutions. So in this case, the circle can be broken down into two different pieces. Right? So the top piece here, you have the solutions of the form y equal to positive square root of 25 minus x squared, given that x is between -5 and 5. Because y is written explicitly in terms of independent variable x. Therefore, you say that this is an explicit solution. Now, similarly, you have this bottom semicircle, and the solution will look like this: y equal to negative square root of 25 minus x squared. Okay. So this, again, the value of y is written explicitly in terms of the independent variable x, and therefore this is an explicit solution as well. For x in this case is between -5 and 5. So this is also a representation of explicit solution. All right, so quickly, just recap what we just do here. So this is called an implicit solution because y is not written as explicitly in terms of x. These two cases represent explicit solutions because y is written as explicitly in terms of independent variable x. Okay. Now for initial value problems. So we are often interested in problem in which we seek solution y of x of a differential equation so that y of x satisfies described conditions. So on some interval I containing x0, the problem solve the differential equation subject to initial conditions. So we solve dny dxn. So this indicates the nth derivative, right? So we see this set up in the last lecture already. This is equal to f of x comma y prime comma y double prime up to y to the n minus 1 derivative subject to y of x0 equal to y naught, y prime of x0 equal to y1, so on and so forth up to the the n minus 1 derivative of x0 equal to y sub n minus 1. So you say that in order to solve differential equation, in this case the nth order differential equation, it's required you to have n minus 1 initial conditions, where y0, y1, y sub n minus 1 are arbitrary, specifying real constant. That is, it depends on what you have, it depends on the scenario of the problem that you're dealing with, depends on the differential equations. So all of this is called an initial value problem, and usually denoted as IVP. So the setup here, all this setup right here is called the nth order initial value problem. This is the nth order initial value problem. Okay. And what we see right here, all of this information is given to us is called the initial condition. More specifically, when you talk about the first order initial value problem or the second order initial value problems, here what you have. For the first order initial value problem, what you do is you solve the differential equations of the form dy dx equal to f of x comma y. So this is just the first order differential equations. And to do this is subject to the initial conditions, y x0 equal to y naught. So the first derivative or the first order differential equation require only one initial condition. Okay. Now for the second order differential equation or the second order initial value problem, you solve d square y dx square equal to f of x y prime subject to two initial conditions. So y of x0 equal to y naught and y prime of x0 equal to y1. So think of this first order differential equation is that you have the velocity, right? And you want to find the value of y, which is the position function. What you need to know is what is the initial positions that you're in. Okay. Now for the type of second order differential equation or the second order initial value problem, this is think about the acceleration functions. Right? And to solve for that, to get the position function y, what you need to do or what you need to know is what is the initial location or position and what is the initial velocity. Okay. So let me quickly correct myself here a little bit. So this is the nth order initial value problem. It's required n initial condition, not n minus 1 initial condition. I'm sorry about that. So it requires n initial conditions, very similar to this, right? So first order, so order one, you need one initial conditions. Order two, or the second order, you need two initial conditions. And of course, for the nth order differential equation, you need n initial conditions. So sorry about that. So solution techniques. So in learning differential equations, we're going to spend a lot of time and effort learning how to solve differential equation or the initial value problems analytically. Right? So we have a lot of or many solution techniques that help us tackle different type of differential equations. So the first approach that, well, most of the approaches that you see in ordinary differential equation course and analytical solutions approach. So you can solve differential equations analytically, right, or analytical approach. However, not all of the differential equations you see that's solvable. Right? Sometimes it's impossible to solve differential equation, even for the first order differential equation. We'll see some of that in the next lecture or two. So when you cannot really solve for the solutions analytically, what you can do is that you can analyze the differential equations and you obtain some qualitative information. Okay. You can sketch out the solutions curve. You can sketch out certain informations to understand the behavior of the solutions, even though you cannot solve the differential equation explicitly. Right? So another approach that you can use is qualitative approach. And let's say some of the problem is very difficult to analyze by hand. You have to use other approach, and another approach is you have to use code. You have to use computer to help you learn about the how the solutions behave numerically. So you have another approach here is the numerical approach. In this course specifically, we're going to use analytical approach and qualitative approach. There's another course, at least in Bridgewater State University, you have a course called numerical methods. That is Math 415. In numerical method, you explore different numerical methods to solve differential equation. Again, there are certain type of differential equation is impossible to solve. Okay. So for analytical solutions methods, here are some of the methods that we're going to see. In lecture 4, you're going to see separation of variables to solve for the first order differential equations, integrating factor, exact differential equations. There's all the techniques as well, including substitution and transformations, but I don't think we have time to do that. But I will consider that into my preparations. But for the first order differential equations, separation of variables, integrating factor, and exact differential equations. And for the second order differential equation, you have method of characteristic, reduction of order, undetermined coefficients, variation of parameters, and Laplace transform. Even Laplace transform can solve the first order differential equations, but it's just more straightforward to just use that for the second order differential equations. Okay. So those are the analytical techniques that you're going to see, but we also going to see qualitative analysis that we're going to use in some of the more difficult or unsolvable differential equations. We will talk about direction fields, we talk about phase lines, and I will print out phase planes from time to time. So the first picture you see here is a illustration for direction field and solution curves. So here, direction fields will be used to visualize the first order differential equations. Again, even for the first order differential equations, sometimes it's not solvable. So please forgive me about this first ST, so one ST. So first order differential equations. You cannot really solve the first order differential equation in some cases, but you can be able to draw down something called direction field, and from there you can draw the solution curves. You can learn how the solution behave to learn is there any unusual behavior in the solution at all. So the first one is the direction field and solution curves. So the direction field are the arrows that you see. Solution curves are the curve in blue, red, and green. Now, the second picture illustrates the baseline analysis. So baseline analysis give you the value of the zero of the function f of y along the vertical axis and use the arrows to show where is the function is going to be positive, whereas the function is going to be negative. We will see something similar to this particular graph later when we get to logistic growth. Okay. And the last one you see here is a phase plane analysis. So this is phase plane analysis. So the phase line analysis is also for the first order differential equations. For phase plane analysis, usually used for a visual display to the 2D solution of the system of differential equations. So phase plane analysis mostly used in system of differential equations. To avoid confusions, right, you can actually turn the second order differential equation into a system of differential equation and use phase plane as well, but I want to avoid that altogether. I just want to use phase line for the first order differential equation, and then phase plane is for the system of differential equation. I don't know we have time to do some of this later on in the course. Again, I mentioned that before that I hope we do. This is very cool analysis to know. But qualitatively, you can use direction field, you can use phase line analysis and phase plane analysis to visualize the solutions to differential equations. All right, that's it for me for the second lecture. For lecture 2, it's about solutions and initial value problems. In this lecture, we also go over some of the terminologies about general solution, which is a family of functions, a particular solution when you know the exact value of arbitrary constant. We talk about initial condition. With different initial condition, will give you a different value of C. Right? You'll be able to find a different value of C. We go over some example how to verify a given functions to be a solution to a differential equation. We talk about explicit solution and implicit solution. We talk about the initial value problem. Again, the idea for this course is that given a differential equation, given initial conditions, can you solve it? And the setup for the initial value problem is shown right here, right? So you have n order initial value problem indicate that you have n order differential equation in n initial conditions. And to simplify this setup, we talk about first order initial value problem. This is the first order differential equation, and it requires only one initial condition. For the second order differential equation with the second order initial value problem, you have a second order differential equation and two initial conditions. We talk about different analytical techniques that we're going to learn down the road and qualitative techniques. Right. And for numerical methods, again, there's another course for that.